To Akiva Solemani.
Hello everyone, I'm Akiva. I was a maths teacher for 40 years, retired now. I taught in secondary schools and further education colleges and universities. And I'm particularly interested in the history and philosophy of maths. And I'm particularly interested in this mathematician Pythagoras, my favourite mathematician. Pythagoras was a Greek philosopher, a mathematician. Philosophy in those days covered virtually everything really, you know, all the sciences, what we now call psychology, sociology, it all came under philosophy. He was born around 585 BC on the Greek island of Samos. This is a bust of him. Now, Bertrand Russell said of Pythagoras, "I do not know of any other man who has been as influential as he was in the sphere of thought." And Pythagoras was intellectually one of the most important men that ever lived. He lived in the same period as Confucius and the Buddha. Amazing period in history, they're all alive at the same time. He travelled extensively, learning from philosophers and mystics in Egypt, Babylon, India and Persia, as well as Greece itself. He became a revered figure, and many stories and legends grew around him. Many people regarded him as a semi-divine person. Now, he was so revered and popular and regarded as so important that even coins were minted with his name and figure on it. He taught and believed in metempsychosis, or the transmigration of souls, a sort of reincarnation. The story is told of him telling a man to stop beating his dog because he recognised the voice of his relative in the dog's whine. This is mentioned in Shakespeare in Twelfth Night. Clown, what is the opinion of Pythagoras concerning wildfowl? Malvolio, that the soul of our grandam might happily inhabit a bird. The story was told of him passing a blacksmith and hearing him hit the anvil with hammers of different weights. Some sounds were harmonious, but one hammer wasn't. He went in and weighed the hammers. He found that the hammers that were in whole number ratios to each other were harmonious, but the other one wasn't. Now this whole number thing is very important, as what comes later. From this he worked out theories of music. Notes that are in whole number ratios to each other are harmonious. For example, he found that if you halve the length of a string, the note goes up an octave. Now, the belief in those days was that the sun, the moon and the planets were each embedded in the rim of a crystal sphere that rotated around the Earth. And the fixed stars were all embedded together in one other sphere. Now, each sphere made a swishing sound with an individual note for each sphere. Because this sound was constant, it didn't register with people because it was always there. They weren't aware of it. Now, the belief was that only the master, only Pythagoras himself could hear it. Only he could hear the music of the spheres. You might have heard this phrase, the music of the spheres. So, my brother-in-law put this together. He's a great musician. This is what it would sound like represented on a piano. Of course, I didn't believe that there was a piano up in the sky, but this is what it would sound like, the separate notes. But of course, all these were going on at the same time, so it was one note. So that sound was meant to be what the music of the spheres was, that only Pythagoras could hear. Obviously it's rubbish, but this is what the belief was at that time. In mathematics he discovered many theorems, very important theorems in maths, and was in the habit of sacrificing a bullock if he discovered a particularly important one. When he discovered a theorem that is still 2,500 years later known by his name, Pythagoras' theorem, he was so pleased he sacrificed a hecatomb, it's 100 oxen. Waste. that was odd considering he advocated vegetarianism. But he realised the importance of that theorem for maths. Right, what is Pythagoras' theorem? If you have a right-angled triangle, if you draw a square on each side, then the biggest square is equal to the other two squares, the areas. So the area of the red square is equal to the area of the green square plus the area of the yellow square. And using algebra, instead of squares, you could say a squared plus b squared equals c squared. The square just means the area of the square. Right? So, for example, a triangle with sides 3, 4 and 5 would be a right angled triangle, because the yellow square is 3 by 3, 3 times 3 is 9, the area of that is 9. The green square, 4 times 4 is 16, and the red square, 5 times 5 is 25. And you see that 9 plus 16 makes 25. Now this is very useful in maths, because if you know two of the sides, you can calculate the third side. Now, if the other two sides are just one unit, say 1 foot or 1 inch or 1 whatever, then the yellow square will be, the area will be 1 times 1 is 1, green square 1 times 1 is 1, so 1 and 1 is 2, so the red square, the area of the red square must be 2. That means that the side of the square must be the square root of 2. The square root of 2 times square root of 2 gives you 2. Now you'll see why I'm talking about this later on, the square root of 2. Now square root of 2 works out as 1.4, it goes on forever, doesn't repeat. Now, I've discovered a theorem myself, you know. Here, if you draw a right angled triangle, and you draw a circle inside so it touches all three sides, where it touches the longest side, it'll split it into 2 bits. Well, one bit times the other bit always gives you the area of the triangle. Now, I didn't want to be big-headed or anything about it, so I thought I'd just call it Solemani. Actually, I'm a big bit of an arsehole. I'm sure throughout the centuries, lots of mathematicians have discovered this. I can't really call it Solemani's theorem, but I did discover it for myself, and there's no record of it, and I did discover the proof for myself, so I thought, sod it, I'm going to call it Solemani's theorem. Anyway, I digress. Pythagoras developed a cult following. He set up a group called the Pythagorean Brotherhood. Now, women joined as well, so perhaps it should be translated as Pythagorean Fellowship. Now, he was their master, their guru. It was virtually a religion, although the thing they worshipped was number. That sounds very odd, worshipping number. What does that mean? Pythagoras taught that everything can be explained through numbers, whole numbers. The basic simple numbers, 1, 2, 3, 4, 5, those numbers. Whole numbers were like we regard atoms as the building blocks of everything. Now what about fractions? Well, fractions was simply the relationship between two whole numbers. The ratio of one whole number over another whole number. So a fraction is one whole number on top, one whole number at the bottom. So they believed that every number could be expressed as a fraction. So they believed that all numbers were rational numbers. Rational meaning ratio, meaning it could be a fraction. Now they had a sacred symbol, the 5-sided star, the pentagram. Now this star is made up from the diagonals of a pentagon. If you draw a pentagon, a 5-sided shape, and you join the corners, it's the pentagram. Now the ratio of the diagonal to the side of a pentagon works out to be what is called the golden ratio, or the divine proportion. What does this mean? Well, it can be explained this way. If you have a line, what they regard as the aesthetically perfect place to cut that line will be like this. The A length over the B length is the same as the whole line over the A length. This ratio is given the Greek letter phi, as opposed to pi, which do the circles. Now, I won't inflict all the working out for you, but it works out to be this number, 1 plus root 5 over 2. which works out to be 1.61. Goes on forever, doesn't repeat. Now this golden ratio can be applied to rectangles as well. This is a golden rectangle. So the A length over the B length is the same as the A and B together over the A length. Now this phi number has been used in many cultural areas for aesthetic reasons. For example, in architecture, Notre Dame, the Taj Mahal, the Parthenon, lots of others all use this. For example, the Parthenon, this is a pictorial representation of what it would have looked like. That's the golden ratio, the golden rectangle. Many artists have used it. Dali, Da Vinci, Mondrian, lots of others. For example, Salvador Dali, Sacrament of the Last Supper, that's the golden rectangle. Even composers have used this phi number in their works, in the arrangement of their notes. Bach, in Goldberg Variations, Mozart, Beethoven, first movement of his Fifth Symphony, and others. So it occurs quite a lot in lots of cultural areas. Now, with their belief in whole numbers, the Pythagoreans believed that any two numbers are commensurable. What does this mean, commensurable? That means that any two fractions could be expressed with the same bottom number. For example, a half and a third. You can make them both into sixths. A half is 3/6, a third is 2/6. Remember from school, common denominator? This just means make the bottom numbers the same. Another example, 2/5 and 3/7. You make them both have 35 as the bottom number, by multiplying the two bottom numbers together. So 2/5 is the same as 14/35, 3/7 is the same as 15/35. So basically they believe that everything could be expressed as a fraction, and all fractions could be made to have the same bottom number. Then disaster struck. Dun, dun, dun. One of Pythagoras' students, a smart ass named Hippasus, discovered numbers that were not commensurable, numbers that could not be written as a fraction. For example, Hippasus proved that the diagonal of a square is not commensurable with the side of a square. In other words, he proved that the square root of 2 can't be written as a fraction. He proved it. So if you've got a square with side 1, and the diagonal will be square root of 2. Now you might think, well, surely you could draw a square with a diagonal that isn't square root of 2. It's the ratio of the diagonal to the side. So if the diagonal is 1, if the side is 1, the diagonal will be root 2. If the side is 7, the diagonal will be root 2 times 7. If the side is 10, the diagonal will be root 2 times 10. Right? So, according to Pythagoras, before Hippasus did this, they believed that the diagonal could be a fraction, the side could be a fraction. If they were both fractions, then they could be made to be fractions of the same bottom number. Now, Hippasus came up with this ingenious proof. I won't go into all the working out of it. I'll just explain the conclusion. From the big square, he constructed a smaller square in a special way. Let's see if I can explain this. In the big square, the diagonal's a fraction, the side's a fraction. You can make them both have the same bottom number. In the smaller square, the diagonal has to be a fraction, the side's got to be a fraction, make them have the same bottom number. But he proved that in the smaller square, the two bottom numbers in the small square will be the same as the two bottom numbers in the big square. And then an even smaller square, forever and ever, smaller squares. So you'd have the two bottom numbers always staying the same all the way through, but the top numbers getting smaller and smaller and smaller, because the squares get smaller, which is impossible. You can't have pairs of fractions where the bottom number is always the same, and the top numbers getting smaller and smaller and smaller forever, and still being whole numbers. So this meant that square root of 2 cannot be a fraction. This was a dagger in the heart, arising from Pythagoras' famous theorem. I mean, his theorem was still correct, but he proved that square root of 2 can't be a fraction. What was even more disastrous, Hippasus proved the same thing with the sacred pentagram, their holy symbol. Again, a big pentagon, he drew a smaller pentagon with the same conclusion as before with the square. You'd have the same, smaller and smaller pentagons, bottom numbers are always staying the same, top numbers getting smaller and smaller. Right. So he proved that both square root of 2 and this phi number, this golden ratio, both of them, they can't be expressed as a fraction. They were both irrational. They can't be expressed as a ratio of one whole number over another. Hippasus had discovered irrational numbers, which of course in maths we use all the time now, we don't think anything of it. Now, all decimals that come to an end can be written as a fraction, like 0.75 would be 75 over 100. All decimals that go on forever but have a repeated pattern can also be written as a fraction, because 0.3333 forever is exactly a third. But decimals that don't end and don't repeat cannot be written as a fraction. These are the irrational numbers. Hadn't been discovered before. Now for Pythagoras and his disciples, irrational actually had both meanings now. It can't be expressed as a ratio, and also insane. It was madness. Madness, I tell you. They thought it was just crazy. This discovery completely demolished the very foundation of Pythagoras' whole philosophy, because their belief was that everything could be expressed in whole numbers, and rational numbers can't. Pythagoras' brotherhood or fellowship fell apart. It was disbanded and the Pythagoreans scattered. According to some historical accounts, Hippasus fled and was drowned at sea. Legend had it that he was killed by the gods for introducing the abomination of irrational numbers into the world. And some histories say Pythagoras also fled to Metapontum, which is in southern Italy. I think it's part of Greater Greece then. And he was murdered there in 497 BC at the age of 88. Poor Pythagoras. Anyway, that's the end. I found it a bit interesting.
Well, fantastic.